if the two balls had been set on the edge of a table with a piece of carbon paper flat on the floor beneath the table on top of another piece of paper, so that when the ball hits the carbon paper it leaves a mark on the paper that's next to the floor, then what we would have is, as the balls drop in the different directions, one ball will go off to the left, one ball will go off to the right. I guess maybe if you're facing in the X direction, this is left and this is right. But one ball goes off in one direction, the other ball goes off in the other direction. And from the distance that the balls hit from a position that would be a straight drop from the center of gravity of the two balls, or the center of mass of the two balls at the instant of collision. So if we drop a ball straight from wherever the center of mass of the two balls is at the instant of collision, we get a mark on the paper. Excuse me. Then we allow the balls to hit and fall to the floor. They'll leave two more marks. Now, by measuring the X and Y distance that the ball 1 follows, and the X and the Y distance that the ball 2 travels. Now, let me digress a second. X is measured along the floor and Y is measured along the floor. We no longer think of the drop as being a change in the Y coordinate. Let's think of the drop as being a change in the Z coordinate, with X and Y being coordinates in the plane of the floor. So again, we measure the X and Y distance traveled by ball 1 and by ball 2 as they fall to the floor. Then, if we know the distance to the floor, we can easily determine the time it takes to fall. We, of course, set the balls up so that they hit in the same plane, and therefore both end up with a horizontal velocity with no vertical component to their velocity, and then that makes it easy to calculate delta t. So again, from delta t, the delta x and the delta y for either ball, we can find the x and y velocities of each ball just by dividing delta x by delta t and delta y by delta t for each ball. Then if we know the masses of the two balls, we could find the momentum components. Let's call them p1x, p1y, for the x and y components of the momentum of the first ball, and then of course the x and y components of the momentum of the second ball. So before collision we have some ball of mass m1 moving at a velocity v1b for v1 before, and a mass m2 moving at a velocity v2b, and for the purposes of this experiment let's have this velocity be 0. So before collision we have velocity v1b and a v2 that's 0. And these balls are not going to hit head-on, so that one ball will move off in one direction, the other in another direction with respect to the y coordinate. They both, of course, move in the x direction, the positive x direction. And we have velocities v2 after and v1 after. Now these velocities are indicated with arrows over the top, and the same here. The velocities before have arrows, indicating that these are vector quantities. Before, when we looked at collisions of balls and falling to the floor and so forth, we didn't worry about anything except whether the velocity was in the positive or negative direction. Now we have to worry about whether the velocities, or what the velocity is in the x and in the y direction. So we have these vector quantities that have both magnitude and direction. Recall from your trigonometry that if a ball has velocity v, let's look at it this way. If a ball has a velocity with an x component and a y component, then it actually has a velocity in this direction. And if the x and the y components have the magnitudes indicated here, then the magnitude of the velocity, or the speed, is going to be the length of a diagonal of a rectangle, one of whose sides is vy, the other of whose sides is vx. And this doesn't look much like a rectangle. It's not very well drawn. This side should be parallel to this vector, this side to this vector. In that case, vx will be whatever v is, whatever the magnitude of v is, times the sine of theta, and vy will be the magnitude of the v vector times the cosine of theta. The v vector could be obtained from the x and y components by the Pythagorean theorem. The Pythagorean theorem clearly applies to the diagonal of this rectangle. And also we note that the angle theta is going to be the inverse tangent of the rise over the run, the opposite side over the adjacent. Theta is going to be the inverse tangent then of the y component divided by the x component.